electrical machines, and today we will cover some important parts, and we will discuss about the remaining topics of yesterday, as we have already discussed about starters and the significance of back EMF. Today we will discuss about the two type of starter we have discussed for DC machine. The first one is 3-point starter and the second one is 4-point starter. Before explaining them, I think I'll recall why we need starter. So, what is a starter? A simple device that is used to start a DC motor. And why we need it? Can't it be started normally just as a simple motor and like connecting the supply and it start rotating by itself? This is not possible. The reason is, just think of that in standstill position. The rotor is not running when we just connected the supply, so there will be no EMF. So V minus R, that is equals to I. If this is 0, this will be 220 and this will be about 0.4 or 0.5. What happened to the motor? The starting current is much higher than the rated current. Say this will be equal to, take it as 5, this will be equal to around 440 ampere, and the motor we are using can't even bear it. The winding of the motor just burn out and there will be smashings of, and what I say about it, just say the motor is damaged. So what we do with the starter is that provide the starting resistance to the motor. If the resistance is increased somehow, say V upon R, that is winding resistance, and RS, that is start resistance, say this is about that capable, so 50 ohm at the starting, and it will become and it's about nearly 4.4 approx. So but say the starting current is limited, and if the permanent resistance is connected to the motor, when the EMF is generated, 220 minus 218 upon 50.5, it will be 2 upon 50.5. The current will be very low. See, I'm saying very low because it will be around 0.04 ampere, and that is much higher as we think. So a starter does to provide a starting maximum resistance and cut it by moving the handle. How it works? Say I'm firstly explaining the 3-point starter. This is the center of the handle. It is at off position. This is the handle, and this is a magnetic pole, say S. This is an imaginary axis where the complete supply is connected to the motor. This is the strip for connection to rotate the handle, and here, 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 here are the resistances. Which are connected in series. Here is NVC. NVC stands for no volt release coil. Now, here is a connection which goes to NVC. To complete the circuit, this is OLR, which stands for overload release coil. This is a magnetic plunger which get magnetized when a suitable amount of or a minimum requirement of current make it energize and magnetize. So this is the basic structural diagram of a 3-point starter. So let us recall. This is the handle. These are the resistances. The starter provides maximum resistance at this point. It is the point where supply is connected, say positive of DC supply. This is the point where armature winding is connected, and this is the point where field winding is connected. We are taking the shunt motor as a reference. We will denote the armature winding terminals A and AZ and A and AA, and for the field winding we will using Z and ZZ. So the positive of supply is connected to L. So the current starts through L and goes to OLR. At starting, the current is low, so the OLR magnetism is low, and the current passes to the plunger and goes through the resistances. Here all the resistances are connected in series, so maximum resistance is there. When we move the handle, minimum it will cut that resistance, and by slowly cutting the resistance at starting its maximum resistance, the motor will not run. Simply when we slowly cut the resistance, minimum current will flow through it, and motor starts rotating as minimum current flow through this, and from this to this, the field winding and the armature winding both get energized. And by completing the circuit and making the plunger to hit there, the NVC which is supplied by connecting to the arc. Say this is a metallic strip, and when this plunger or handle run on the arc, it is connected to the NVC, the no volt release coil, which is here to just attract and make the plunger to just hold there. If it get fixed here, then continuous supply will reach field winding and armature winding. Motor will start running. At the time of some fault, say the current is increasing somehow, overload release coil will act, due to which it completes the circuit by connecting here and here. The current will go to here and no volt release coil found, no path, due to which it just completely demagnetize and release the plunger, which suddenly came to its off position and increased the resistance to save the machine. The machine gets shut down automatically. This is complete about 3-point starter. However, in a 4-point starter, the no volt release coil is having a R connection. See, this is the point. Here, a connection is also obtained to provide resistance at the shunt. This is the resistance R. This will increase the efficiency. Now, for the next topic, we are doing losses, which is one of the most important topics in machine, in every kind of machine. So, what can be the losses? First one is copper losses, second one is iron losses or core losses, and third one are mechanical losses, say windage losses or losses due to friction of bearing, or just like that, there are only two. So first one are copper losses. There are 5 type of copper losses. First are armature copper loss. The formula for finding armature copper losses are simply Ia square Ra. Second one is shunt field copper loss. ISH square RSH. Series field copper loss. That is ISC square dot RSC. Fourth one is interpole winding. Copper loss. Ia square Ri. And the last one is brush contact loss. Brush contact losses. That is Ia square dot Rb equals to 2Ia Vp. Now, there are 5 type of losses, but we can simplify into armature copper loss and field copper loss, and we have already discussed the full. Now the second one are iron losses. These occurs in the iron parts or the core of machine. There are 2 types of this again. First one are hysteresis loss. This loss occurs due to reversal of magnetic flux in our magnetic material. And what magnetic material we are using? That is silicon steel. So the formula for this is that is hysteresis loss pH and equal to kh, that is hysteresis loss constant, or I'll say energy loss per unit volume of magnetic material. And here is V, the volume of magnetic material, and F, the frequency of reversal of magnetic cycle, and B, the magnetic flux density have the power 1.6. The unit of it is Tesla. These losses these losses occur in armature of machine mostly. And to reduce these losses, what we do is using a simply CRGO steel. What is CRGO? That is cold rolled grain oriented steel. By some chemical processes and using special materials, we will modify the silicon steel into CRGO steel. The second one is eddy current losses. So, firstly, what we know about eddy currents? What are these? As we know that due to change in magnetic flux or by cutting of magnetic flux linkage, there is an EMF induced in the conductor, and if a closed path is provided to the conductor, a current I will start flowing in that conductor. That current is known as eddy current. These eddy current are responsible for eddy current losses that appears in form of heat. So the formula for eddy current is that is PE, the eddy current losses, equal to the eddy current constant, whose value depend upon the nature of magnetic material, the volume of magnetic material, the frequency of reversal of magnetic cycle square, the thickness of lamination squared, and the square of flux density. What we do is just using the lamination, which is around 0.3 to 0.5 mm thin. These losses are directly proportional to square of thickness of laminations. So the third one losses are mechanical losses, and we have discussed about them, that are windage losses. Say when we run a motor, a fan is connected on the shaft to just throw the heat generated in the motor outside. And when this thing happen, the air just act as an opposition to the rotation and also apply some weight on the shaft. This somehow produces some losses, as some a little bit power is consumed in form of that opposition. And second one are friction losses. Now, to avoid these losses, We just lubricate the bearings or say these parts. Now what we do is simply read about more losses. These are special ones. First one are constant losses. These losses do not change with change in load or anything. Or I'll say the losses that occur constantly at every time. These are iron losses, mechanical losses, and shunt field copper losses. They didn't change. And second one are variable losses. These losses change with change in supply or excitation. These are armature losses, all the armature losses. And the third one are stray losses. What are stray losses? These are simply the sum of iron losses and mechanical losses. So here we are done with losses and starter part. Now what we do is start the characteristics of DC machine. So firstly we will discuss about the characteristics of DC generator, and after that we will discuss about the characteristics of DC motor. So as we have studied that there are three types basically that are used in system. Are there three types of generator? And there are two type of characteristics we will study. First one is no load, that is same for both or say every machine. No load. No load. Characteristics. And these are also known as magnetism characteristics. We will discuss about them in detail, why they are known as magnetism characteristics. And also we will discuss about the concept of voltage buildup. And the second one are external characteristic. These are also known as on load characteristics. Sorry for the writing. So firstly just taking a shunt motor, say this is our ammeter, this is voltmeter, the armature winding, the field winding, applied voltage, the terminal voltage, generated voltage Vg, and it is rotated by a prime mover. So these are drawn between the field current and generated EMF, or say induced EMF. So before starting, I have a question. If there is no load connected, did the current flow takes place or not? It's a simple question. However, I am the only one to answer. Right now, in the situation, I am not able to connect to you people. But however, see, as an open circuit, the current can't flow, as it only flows when it got a closed path. So, as no load is connected, the current when the prime mover is rotate made the generator to rotate, it the EMF is generated, and when it's generated, the current flowing through it will never go to this side as it's open circuit. The complete current go to field winding. Now here's a concept. As we have discussed that the field current is very low, and the reason is the resistance of field winding is very high, that is required to just magnetize and generation of magnetic flux to cut by the armature and generation of EMF. But what if the complete current that is generated by the armature goes to field winding? So when it goes to field winding, the current IF increases. That made the flux of field increases. As the much the current will go to field winding, the much the flux is produced. Now, if the flux is more, then EMF is also more. As we have discussed that EMF is directly proportional to flux. And if EMF is more, the current of field is also more. This process takes place till the saturation point is achieved. This is IF, this is EG. Say at starting there is residual magnetism, and firstly the EMF goes down, and after that it starts increasing. This is the maximum point, or say E set, the saturation point, the maximum generated voltage. And that's why, because in a magnetic material, the amount of magnetic field produced or magnetic flux produced is at its saturation. Everyone have a limit. So it is the maximum amount of flux it can produce, no matter how much current will flow through it. So at starting, we have seen that there is downward curve of this. Why this? Why so? This is because the is residual magnetism in starting opposes the main magnetic field, and this is the sign of opposition. As we see, the curve is downward, so the actual magnetism is going down at the starting, and when the residual magnetism goes in line and the current increases, the flux produced increases, the main magnetic flux will also increases. So the current increases, the EMF increases, and it will reach its saturation point. This is same for every motor, and this is also known as voltage build up. So for the shunt generators are external characteristics. So this is the field winding. This is a meter. These are drawn between terminal voltage V and armature current. So this is the load. So when the generator is rotated, an EMF is induced, and what happens? Say EMF induced, and it goes through the load and completes the circuit by say first one load is on. Now we will increase the load. By increasing the load, see, as Eg is equal to V plus IaRa plus brush loss. So neglecting brush losses, when we increases the load, the line current IL increases. If IL increases, then Ia equals to IL plus If. If it increases, Ia also increases. And if Ia increases, the IaRa losses increases. And if this amount increases, then this amount will decrease. Eg decreases. So the generated voltage will decrease. And if further we increase the load, the more the load current, the more the armature current, the more the losses, and the less the induced EMF. And at a point, the induced EMF will become, and the induced EMF reaches its breakdown point. See, from it is the saturation point of EMF, E naught. This is Ia armature current. First it will come downward due to losses, and at this point it will completely shut down. This point is known as, say, name it A, and that A point is known as breakdown point. So, and we will discuss furthermore concept about that, which is if we increases the load. See in this diagram about that. What happens if armature increases? The armature reaction, say the field of armature also increases. and armature field will start to disturb the main magnetic field. We are taking here the demagnetizing component, the armature reaction increasing, due to which the demagnetizing component, that is Fd, also increases. If Fd increases, the magnetic flux will decrease, and magnetic flux decrease results in decrease of generated EMF, and that thing will affect it in the same way, that causes its breakdown point. So what basically is breakdown point? The point at which the demagnetic flux is equal to and opposite to the main flux, then eventually there is no EMF generated, making the generator to shut down. So today we have completed our topics on starter, the losses, and we have started the characteristics of generator. The further characteristics of generator for series generator and compound generator will be discussed in the upcoming lectures. That's all for today. And after completing the generator part, we will move on to some numerical problems related to generator. I think that the numerical portion will be going to held on Sunday. So there can be two lectures on Sunday comprising of half of parts. See, there can be a long video that can be uploaded at a time. So due to this issue, I'll just divide the lectures and do the numerical portion. As in the gate syllabus, I have gate syllabus. See, for DC machines, we have completed separately excited, series shunt, motoring and generating mode of operation, and their characteristic speed control of DC motor. According to gate, we are near to our completion of DC machine. However, the characteristics are remaining, and the speed control is also remaining, and this is for motor. So I think we will discuss about them after Sunday. If there is any problem regarding it, I'll just shift the lecture. So thank you guys for watching the video. Thank you.